Hello, welcome back. Let's continue with our lecture on general theory of relativity. In the last lecture, we have seen basics of inertial frame and Newton's laws of motion. And let's continue. In this lecture, we are going to consider more of invariance of Newton's laws of motion, and that is called the Galilean invariance. It was the Galileo who was first realized that the laws of physics have to be same everywhere, no matter where you measure. So this principle is generally called principle of covariance. The principle of covariance states that laws of physics should be same everywhere, no matter what coordinate system you use, what reference system you use, or where you do the experiment. So physics cannot change from point to point. This is the first abstraction which was developed by Galileo, gives a very important step forward in making the laws of physics abstract. Now, in comparison with his contemporaries, Galileo had a much better understanding of universe, mainly through the instrument like telescopes and other observational abilities. He understood that the universe is far vaster, and it is impossible to have uh, a good understanding of universe if laws of physics changes from point to point, say from Earth, Jupiter, Saturn, or some other galaxy or some other place. Nowadays, people even talk about parallel universe also. So laws of physics have to be same. So that is called the principle of covariance. Now, when you write in terms of equation and a certain coordinate system should look same form written in an equation, that is called the principle of invariance. It means we have seen that the Newton laws of motions look same in all inertial frame. That means Newton laws are invariant under the inertial transformation. Laws are not generally covariant because they are not invariant under an arbitrary coordinate transformation. So this idea is very important. We will not go into general covariance at this stage, but it's very important for the relativity. Let's look at the Galilean invariance, how the idea developed, and how we go away from the inertial frame to non-inertial frame, what kind of modification or what kind of computation is required, and that is what we see in this lecture. And let's continue with the lecture. So this is naturally dedicated to Galileo for his phenomenal work on the invariance of inertial frame and what generally now referred to as Galilean invariance. Let's start with the role of coordinate system. The coordinate system or basis vector serves a framework to formulate the laws of physics, as we have already seen that the forces and the velocities are already vectors, and we can have more complex laws of physics such as electromagnetism, field theory, all are expressed in terms of the vector fields, and coordinate system or basis vectors forms the basic framework for expressing the laws of physics. Since the coordinate system or related mathematical rules are basically framework, and laws of physics should not depend on the coordinate system, because physics is the one which we are expressing in terms of the mathematical framework, and that framework should not dictate the physics. On the other hand, we should be able to use suitable tools and then apply them to understand the laws of physics. So physical law should not depend on the mathematical framework, that is a coordinate system or basis vectors which we are using. So this principle is called the principle of covariance. Laws of physics should not be changing based on the coordinate system or the framework which you choose. However, we have already seen that Newton's laws have a weak point, that in order to apply Newton's law, what we need is a inertial frame, and inertial frame is not a generally covariant. That means it is means the Newton's laws do not look same in all coordinate system. So this makes it somewhat difficult. However, basic idea has to be further explore to see how we can apply principle of covariance. If Newton's law themselves are not invariant under arbitrary coordinate system, then what is the point talking about principle of covariance? We'll have a look at all these things. Newton's law follows a limited version of covariance called the Galilean invariance, where we could exploit this limited freedom. However, we can see how we can explore possibility of extending the Newton's law beyond the simply Galilean transformation in general to arbitrary coordinate system. So that also is a very useful way of expressing the Newton's law. Let's try to understand this through the coordinate system. Because of the inherent simplicity and the straightaway applicability of Newton's law, Cartesian coordinate system gives a good starting point for understanding all the coordinate system. Once we express the laws of physics in Cartesian coordinate system, then we can transform them to any given coordinate system. Then we can see how it changes or whether it remains invariant under coordinate transformation. Now, Cartesian coordinate system is based on two very important mathematical aspects. The first one is basis vectors are orthonormal and constant. They do not change from place to place. In Rn, if you have a basis vector defined at each point, then they are constant. The Cartesian basis vectors are given as in 3 dimensions. There are 3 linearly independent orthonormal vectors. They are E1 is equal to 1, 0, 0, E2 is equal to 0, 1, 0, and E3 is 0, 0, 1. It's straightforward to see that they are constant as well as orthonormal. Given any vector T, it can be expressed in terms of a basis as a T is equal to sum I going from 1 to T, Ti, Ei. This in general can be extended to arbitrary coordinate systems. Since Newton's laws are applied only in 3 dimensions, we talk about a 3-dimensional vector space. In general, all the mathematics goes through for arbitrary n dimension. So Ei's are bases and the Ti's are the component of vector in that basis, or with respect to that basis. So we express our laws of physics in terms of the vector. That basically means we fix our bases and write them in terms of the component. That is what. And the dot product in space is given in terms of a simple quadrature. That is, for any given vector, u and v in the Rn, the dot product, the Euclidean dot product is given as u dot v, that is also equal to v dot u is equal to I going from 1 to 3 ui vi. This also can be written as simply u1 v1 plus u2 v2 u3 v3. So this is the first concept of distance given by Euclid, and which leads to the complete geometric understanding of Rn, which is described by the Euclidean geometry. So this is a portrait of a Euclid. Let's continue with the coordinate system, and what we have is a coordinate system in which each point is represented by 3 tuples which are given as a coordinate of the system. That is, x is given as a x1, x2 and x3. In terms of the basis, they can be expressed as a x as a x1 into E1 plus x2 into E2 and x3 into E3. So this is a general way of representing in terms of the basis. Sometimes it is used as a ex, ey, ez. For the convenience of further notation, we use a number so that it can be easily generalized to arbitrary degree of freedom. So here the magnitude or the length of the vector is also given in terms of the Euclidean distance, that is equal to square of the distance is given as a x1 square plus x2 square plus x3 square. So this comes as a perfect square. So that is a basic idea of the Euclidean distance. Based on the physics you want to study, you can define a vector's field in this coordinate system. So that is basically what we do. Now, if we want to study the motion of a particle under the influence of force, that is Newton's laws of motion, then vector field which we are interested in is the force, which is already given to you in terms of component F1, F2, F3. Now we have a dynamical quantities, which first comes is the trajectory of the particle, that is the position vector of the particle as a function of time. This is represented in terms of three component x1, x2, x3, all function of time as particle moves. So its components or the position vector keep changing, represented by the curve gamma. Now we have a curve represented by a parameter t given with the position x. We can also have a tangent vector, that is what we call is a velocity, or x dot, usually represented by v, as a velocity which is x1 dot, x2 dot and x3 dot. In this case, we have already seen the advantage is that the vector, the basis vectors do not change with the time. So this leads to only change in the component, and that is what we call is a velocity. We can also have an acceleration, second derivative of the components, that is x1 double dot, x2 double dot and x3 double dot. These serves as a acceleration of the part. Basically, Newton's law is relating all these things, and that is what we have seen, that the F is equal to m into x double dot. So that is what we have is a Newton's law. It is written in Cartesian coordinate system. Now we can do a coordinate transformation. That is the basic idea, that once we express the laws of physics in specific coordinate system, we have a freedom to change the coordinate system. The coordinate system may or may not leave the laws of physics form invariant. That means the form invariance is simply means that the laws of physics or the equation of physics which look same in every coordinate system. For example, Newton's law, when we write in a Cartesian coordinate system, we simply have the form that the m into x double dot is equal to f. So this is a form invariant. Under inertial transformation, Newton's law would look same. On the other hand, if you have an arbitrary coordinate system, then we got to see how the laws are going to change. Basic idea here is that the often looks simpler on a specific coordinate system. Not all coordinate systems are suitable for doing all calculations. So that is why it is important to have other coordinate system than Cartesian coordinate system. Otherwise, we would have simply stuck to Cartesian coordinate system and did all calculation. Given the symmetry or the nature of the force, it is not possible to solve all problem in a Cartesian coordinate system. So that is why you need to have freedom on which you're doing all calculations. Let's say that we have a inertial Cartesian coordinate system, which we refer to as O1, which is represented by coordinate x1, x2 and x3. So we want to transform it to a new coordinate system, which we call is O2, which is given by xi. Xi again is a three-dimensional, so you have a xi1, xi2, xi3. You can make it an arbitrary, but the coordinate transformation, if it has to be 1-to-1, then both the dimension have to be same. Otherwise, there is not going to be 1-to-1. You will have some projection. So we have a transformation, that means we can express the coordinate in terms of other. So we have a bijective relation, that is all the xi's should be able to express in terms of xi's. Same way, all the xi's should be able to express in terms of xi's. So here we have in O2, xi1, xi2, xi3 can be expressed in terms of x1, x2 and x3. And the same way we can have a reverse. In O1, we have a x1, x2, x3 is expressed in terms of xi1, xi2, xi. Now, for the convenience, we can take a specific form of coordinate transformation, which is very popular, which can be written in terms of a matrix if you wish. I do not want to bring in the notation of matrix. We use indices, which is more convenient. So the coordinate transformation which we are talking about is given x1 as a alpha 1, 1, xi1, alpha 1, 2, xi2, alpha 1, 3, xi3 plus beta. So we have this coefficient which relate xi1 and x1. Same way we can have x2 and x3. Here we have a 3 into 3, that is 9 coefficients of alpha, and 3 betas, that is a total 12 component is there in this transformation. Of course, we can write this in a compact notation. We are still keeping a summation convention. Xi is equal to sum j going from 1 to 3 alpha I j xi j plus beta I. So I going from 1 to 3 and j is also going from 1 to 3. This allows us to relate. We could also have a reverse relation, that is we can write xi I in terms of xi, and we can have a very similar relation, and all that can be seen. But now let us go through this first set of relation and try to relate the acceleration in the two coordinate system, how they can be related, whether we can make some sense. So the velocity and acceleration in O1 are given by xi dot and xi double dot. Now we got to relate that to the velocity and acceleration in O2 given by xi I dot and xi I double dot. We have the relation here, xi is related to xi I, alpha ij and beta I are the coefficient. So this is the relation between the position coordinate. So we can differentiate this and find out the velocity relation. Because if the alpha ij and beta i's are constant, then we have inertial transformation. But for the sake of better understanding, let's keep them to be general. They are changing either place to place or time. So that means alpha ij could depend on the position as well as time, same way beta ij. So they take part in the derivative, and then we have three terms for the velocity of the particle. That is how we can relate the velocity. It's a simple differentiation using the chain. We can differentiate it again, then we get more term, but essentially straightforward step. We have x double dot related alpha ij double dot, and then we have a alpha ij dot and xi j dot. Then we have a transformation of acceleration itself, that is alpha I j, and then beta I double dot. So this is how we relate the acceleration, and this looks somewhat cumbersome with all the summation and so on. This is a main relation between the acceleration in the O1 and O2. Now here is a good time to use the Einstein summation convention, because equation already having a lot of terms and summation, we can get rid of summation. Basic idea is that summation is done over the repeated index, and that summed over the dimensions of the space. In this case it is 3. Summation is over the repeated index and no difference between the upper and lower indices. In general there is, but currently we are using simple system. We will differentiate them as we go along. Currently in the Cartesian coordinate system we are not distinguishing the upper and lower indices. Now acceleration in this new avatar after using Einstein summation convention looks like this. Xi double dot is equal to alpha ij double dot xi j. That means here j is repeated, that is it is summed over j, and I is a free indices, j is a dummy indices. It is summed over. The second term is alpha dot ij xi dot j. So again it is summed over j, and then third we have alpha ij summed over j, that is xi j double dot. Because j is a repeated index, it is summed over that, and then this is a free term. So this is how the equation gets simplified. You always have to remember that there is a summation implied in the repeated index. Of course, it's much neater than what we have here, the ugly form, what we call. So let us see how we can understand this different term. So what we have here is first is the acceleration in the O1 frame, that is the inertial frame, and then we have the first term which depends on the position in O2, that is related to the position, and the second derivative of the transformation. Now the second term, which is basically depends on the velocity in O2 and the first derivative of the transformation. In the same way, third depends on the acceleration, alpha ij is a transformation, and the last one which depends on the second derivative of beta. So this is the expression which we have, which is somehow you can relate to the terms which you know as an inertial. You have seen whenever you transform it to rotating coordinate system, acceleration will have an additional term which you call as the inertial forces, which are centrifugal and Coriolis terms. You know that the centrifugal force depends on the position, that is in the rotating coordinate system it is given as omega square r. So omega square is essentially equivalent to saying that alpha ij double dot. Then we have a Coriolis force which depends on the velocity of the particle. So whenever you don't have velocity, there is no Coriolis force. This is a Coriolis-like force when you transform it to an arbitrary frame. That is what you get. The third term is acceleration itself, so which is a transform. That is a term which we need. And we can see that the acceleration in one coordinate system is related to much more complicated terms than the acceleration in another coordinate system, all because of the coordinate transformation, which is not inertial. If you have an inertial coordinate system, this all term would go and only one would remain. So that is what leads to Galilean transformation or Galilean invariance. Suppose O1 is a Cartesian coordinate system, and if we want O2 also inertial system, then we have to see what happens to the transformation. There are additional terms which we do not want. The first term, acceleration, which is coming because of transformation depending on the position or velocity, which is we identified with the centrifugal-like force, which should go to 0. The second term also should go to 0 because that is transformation dependent. It depends on the derivative and the velocity of the particle. Last term, which is also not, we do not want because it is related to something depend purely on the coordinate transformation. So that is what leads to this term to be 0. So beta double dot equal to 0 implies that the beta is equal to V naught T plus x naught. So that essentially means that moving with the uniform velocity. So that is a transformation part corresponding to the uniform motion. The first two terms will go to 0 only if alpha double dot is equal to 0 and alpha dot is equal to 0. So if you solve this, you get a simple constraint that alpha ij should be constant. So this is what we earlier talked about. That is a transformation in which the transformation does not depend on the position of the coordinate system. So this leads to what we call is both frame become inertial coordinate system, and we have the two relations, that is the alpha ij should be constant, beta ij should be V naught T plus x naught. This type of coordinate transformation which leaves the Newton's law invariant are called the Galilean transformation, and they are basically given by alpha ij is equal to constant and the beta ij is equal to V naught plus T plus x naught. You already know that the alpha ij represents the rotation. Adding x naught only means the shifting in origin, and the beta V naught is equal to T corresponding to the uniform motion. These are the Galilean transformation which leaves an inertial frame invariant. That means Newton's law remains form invariant, that is x double dot is equal to F. M is also there. I am absorbing M in the x double dot, and that is what is form of the Newton's law, which remains same in all of these coordinate system, and that is what we call is the Galilean invariance. However, you see that this has a very limited application, and we should see what happens if the coordinate transformation is more general and how much complication does it bring in. So this is a story of inertial frame where Newton laws are in a neat form. However, what would be more interesting and practical would be non-inertial frame or the transformation where alpha ij are not constant. Let's have a quick homework problem just to show that how difficult these things get, or how difficult Newton's law get when you do a non-inertial transformation, or the transformation where your transformation depends on the position. So let's take this simple example. You have a Cartesian three-dimensional coordinate. You can restrict it to two dimension. Let's make it life little simpler. You reduce this equation to two dimension, and you have the equation x is equal to r cos phi and y is equal to r sine phi, that is a equation instead of 3 dimension, and same way you have a r square is equal to x square plus y square, and tan phi is equal to y by x. Now you express x double dot and y double dot in terms of r double dot and theta dot. This is a homework problem. You have a 1 week time. You upload it on VLearn just to get some experience how difficult it is to have a transformation done on the coordinate system, such as even a simple coordinate system such as a polar coordinate. Now let's look at this in a little bit more detail. An interesting application of Newton's law required transformation beyond Galilean transformation, as we have seen in the case of a polar coordinate. And the calculations becomes lengthy and complicated. So this is where physicists did not want to do long calculation, or they didn't want to indulge in the vectors and tensor transformation, and that is natural too. But however, GR requires all this. But before that, people have found interesting way of solving Newton's equation. To avoid all these difficulties, one of the method developed was a Lagrangian mechanic, where everything depends on a simple scalar. Once you have a Lagrangian, which is a scalar, which is basically kinetic energy minus potential energy, and that would serve as a one fundamental scalar from which all the equation of motion can be derived. You can see the Lagrangian in spherical polar coordinate is a fairly simple one, and you can immediately get the equation of motion, and all the long calculation which you have done earlier homework would reduce to nothing. So this way you can see also the additional term which depends only on the velocity and depends only on the position. These are centrifugal like and the Coriolis like terms which is arriving in the equation of motion. Also you can see very easily. We'll come back to that little later. So let's, from our point of view, let's ignore the potential energy. Let us see the free space solution where there is no potential. Then Lagrangian becomes simply kinetic energy. That is, Lagrangian is equal to m by 2 into v dot v. So now for simplicity, sometime I will ignore this factor of m by 2, or sometime you just let it go. If you want, you can say that I have taken m is equal to 2. So Cartesian system, what we have is a Lagrangian for free particle is m by 2 vi dot vi, or that explicitly one may write in the Cartesian coordinate system L is equal to x1 dot square, x2 dot square plus x3 dot square. For a simple part, there is a positive sign which is not needed here. Now we may think of transforming these to a non-inertial frame and see how it looks. Basic idea is to move away from the complicated calculations as Newton's law into a simpler way of doing things like Lagrangian. So we start with the Galilean system or Cartesian coordinate system and do a transformation. Once we have this expression in the Cartesian coordinate system, we do a coordinate transformation. Coordinate transformation could be Galilean. In the case of Galilean, it would not change much. We know that transformation of Galilean would lead to Lagrangian, which is simply a exact square, and there is no much interest. On the other hand, if we do a non-inertial transformation or non-Galilean transformation, let us see what happens. So that would be lengthy but enlightening calculation. So let us check how does the simple free particle Lagrangian changes under non-inertial transformation. So we start with the Cartesian coordinate system O1, which is given as x1, x2, x3, and then we transform to a new coordinate system O2, which is given by xi1, xi2, xi3. Now only difference is that the new coordinate system O2 need not be inertial. So that means we have a transformation xi is equal to alpha ij xij plus beta dot. Now compute the velocity x dot. We simply have to differentiate. Now we are assuming that both these transformation coefficient alpha ij and beta ij need not be constant, and then we will have its derivative coming in the velocity. Once we have the velocity, we can simply compute the Lagrangian. Of course, you'll see that the Lagrangian is a square of the velocity. We have to multiply these two terms. Each has a 3 term. There would be 9 terms altogether with a very complex relation. Lagrangian of a particle after the non-inertial transformation, we have a derivative of alpha first, then xi I, xi j, xi k. Then we have alpha ij, derivative of alpha ik, and then xi I, xi k, xi j dot, and so on. So we have all 9 terms given here. It looks extremely complex, but if you are doing a classical mechanics, Goldstein would say that this would be the form of the kinetic energy in a general curvilinear coordinate system. One can factorize them, various things, and for the more detail of how exactly it can be done, you can look in the Goldstein's chapter on Lagrangian mechanics. And what we see is a mess. So it's complicated, cannot be cleanly understood. However, there is a reason for that. This is complicated. One of the simplification happens if we assume that the coordinate transformation itself doesn't depend explicitly on time. Now you see that time is not coordinate here. Unlike relativity, Newtonian mechanics, time is a fixed parameter eternally flowing on its own way. So this is no way is a coordinate system parameter. So if your transformation does not depend explicitly on time, that is some simplification happens. What does it mean? It means that when we differentiate d xi I by dt is equal to 0, the transformation from x to xi I or xi I to x doesn't explicitly depend on the time, but it could depend on the position. In such case, velocity can be written as xi dot is equal to, it's simply a chain rule which you use. You have alpha ij which depends on the position, and then you differentiate and then differentiate the position. That is d alpha ij by d xi k, xi j, xi k dot, and alpha ij, xi j dot plus d beta I by d xi k into xi k dot. So this is the expression for velocity if the transformation explicitly does not depend on the time, which is okay for us because time is not a coordinate, it's only a parameter. Now you can see after cooking up some indices, renaming the dummy indices, we can factorize this. What we get is that xi dot is equal to d alpha ij divided by d alpha xi j alpha ik, and then d beta I by gk into the common term. When we substitute here in the Lagrangian, we simply get a quadratic function in velocity in new coordinate, and all the gik and all that could be position dependent, and their explicitly expression is given by this expression, or it is this expression which relates all the coefficient gik. Gik used for the metric in the differential geometry, but same notation I have used because this in fact turns out to be the metric on your curvilinear coordinate, and these metric coefficients can be calculated based on the transformation. This looks somewhat messy, but this expression can be further understood better by doing proper transformation, not going through the classical mechanics, but directly going into the geometric aspect of the transformation. However, you can see that now earlier you had a clean kinetic energy, which is a diagonal element. In this case, you have all the cross terms coming between the various velocities and so on. This is a way the metric or the kinetic energy coefficient acquire the position dependently. Once you have a Lagrangian, one can simply get the equation of motion by taking the Euler-Lagrange equation for the given Lagrange. I have got rid of some of the constant, which doesn't matter to get the equation of motion, and you can see that you would get a eventual equation of motion. You can transform Newton's law and find out that that it is exactly the same thing which we are going to get. So this is the one way of avoiding the complicated calculation needed for the computing the Newton's laws of motion by simply using the Lagrangian. And now we can also use the arbitrary transformation, not just have to stick to the inertial transformation to do the dynamic in the Newtonian mechanics. The mechanics more or less remains the Newtonian itself because the force is balanced by the rate of change of momentum, but additional freedom we get is the ability to do transformation to an arbitrary coordinate transformation. This is almost like a general covariance where we can write down the equation of motion in an arbitrary coordinate system. So this is a very important step from the relativistic point of view. We'll stop here and we will continue in the next lecture.